probably some variation in the shading on the constant wall. But in terms of simple examples, right? I mean, you guys see cars drive by all the time, right? Have you ever sort of seen, one of these hubcaps that have a lot of spokes? And it feels as if, the wheel and the motion of the spokes, they don't sort of match very well. I mean, they're not moving in the right direction, right? Now that, well, I mean, it's not possible, right? Yeah, I've seen cars where they have these things on some kind of a rotor, right? So it's mechanical, but that's not what I'm talking about. I'm talking about things that are not motorized and they're just moving in the normal direction. Now that is an illusion, right? Why do you think that illusion happens? Very good. So the same reason why we cannot see this light flickering is the exact same reason why we see that moving in the wrong direction, right? So the concept for basic perception is something we call aliasing, right? It's a matter of how quickly we are able to sample something that is changing in time. Right? Now the vision for us, and in general for any artificial sensor that we think about, that phenomena holds true both in space and time. Okay? So our ability to perceive things that exist either in space or in time is entirely dependent on how often we are able to sample a particular event of change. Okay? So if that wall is textured, I cannot see it from out here. Right? I really can't see if that wall is textured. I don't even know if it's textured. You guys at the back might know better. Right? But the reality is that it's not that I am unable to see it if I come close enough to it. Right? If it's textured, if I'm very close to it, I'm able to sample it, right, at a high enough resolution where I should be able to see the texture. Standing so far off, I can't see it. Okay? Just because I can sample it. So the same things happen in time as well in space. Okay? The example of the spoke moving, that's a time sampling example. You cannot see something in space, that's a space sampling problem, right? If you cannot see a certain texture. All right. Now, of course, all of that happens at the sensing process, right? Once we sense something, then there are two levels of processing that we typically distinguish vision processing in. Something that we call low level and something that we call high level, right? Low level processing is predominantly involved in looking at primitives in terms of observations or in terms of useful information that's present in the sampled signal. Okay? And when I talk about primitives, we're talking about things that are defined at a very, very low level, things like, sharp transitions, contrast changes. You have an edge somewhere, right? So a particular color stops and a new color starts. Those kind of changes is what we're talking about in terms of low-level processing. Now, how do you take those small observations and put them into higher abstract concepts, right? How do you say, I look at this chair, right, and I see, well, there are many places where contrast changes happen, right? I see a flat surface here, pretty much, having, let's say for now, some constant illumination. At the edge of it, there's a change, right? This side there's a change, this side there's a change. How do you take all these changes, put them together, and construct a shape? Right? Now that is really what I'm talking about in terms of higher level processing. Right? So you take small primitives, put them together in order to define higher level abstractions, what we call shapes. Right? Shapes is something that we define as a particular kind of geometry. Right? Now if you think of it and think about broader abstractions, we call this a chair. Yes? Think of why do we call it a chair? We call a lot of things a chair. Not all of them have the same geometry, right? Not the same shape. These days chairs come in all kinds of forms. Very interesting artistic creations, come across as chairs. Why do we call them chairs? Function. Very good, right? So there's a specific function involved. Right? The function is, you sit on it. Right? Now, think of how do you take low-level processing to the level of abstraction where you can generalize something to say, you know, this is what I sit on, and as a result, I will call this object a chair. That's a very difficult abstraction, right? If you try to generalize it, that's very, very difficult to do. Now, it turns out, you know, the human brain, in terms of higher level abstractions, tends to build representations from low-level primitives. We don't know exactly how they build it. And at the same time, it feeds off of an internal memory, if you will, right? So, you know, back in the 60s and early 70s, there were studies done on the human vision system in terms of how many distinct objects do humans recognize, right? It turns out, well, at that time at least, you know, the number was roughly in the order of 10,000. At the same time? Yeah, well, not at the same time, but we recognize up to 10,000 distinct objects, right? Now, you know, you sit there and say, well, 10,000 doesn't seem like a whole lot, right? But think of 50 years of image analysis research. What's your best guess as how many objects do you think an artificial vision system is capable of recognizing? 500? Any other guesses? It's actually not even 500. Right? You're talking about a handful of objects. Really. Below 100 objects is what an artificial vision system is capable of recognizing. We still haven't figured out how to take primitives and come up with generalized abstractions. So in terms of human processing, we have a reasonable idea what's going on at the low level, right? So, and the low level is primarily dedicated to your visual cortex, okay? So your visual cortex, you know, your eye sees something, gets sensing, and it sends it back all the way to the back of your brain. That's where your visual cortex is. And that's where low level processing happens. That's where primitives are abstracted. After that, the signal is sent for higher level cognitive processing, and we don't have a very good understanding what happens there. Okay? So as a result, a lot of artificial heuristics as well as algorithms, mathematical models have been proposed of what happens in higher level understanding of images. But those are algorithms and mathematical models. We haven't quite bridged it to the human vision system. Okay? All right, now obviously we do certain things very well, and we do a lot of things without really thinking much about it. Right? If I just throw something at you, right, I mean, most of you here are going to see it, you're going to probably catch it. Okay? That's something that you do as a reflex more often than not. Right? But think of what is involved in actually doing that. It's fairly complex, right? You have to first identify an object that is coming towards you, right? And you're going to identify that object among all the other objects that are present in the room, right? So obviously you're seeing a lot of things, right? But you're going to somehow identify and focus onto that object. You're going to lock onto it. At that point, you're going to actually try to figure out its trajectory. Right? You're going to guesstimate its velocity. Right? You're going to say, okay, the object's coming toward you. You're going to figure out and estimate its size. In fact, by looking at it, you're going to estimate its size and weight. Right? Once you do that, that's when you actually get to trajectory. You're going to figure out when it's going to sort of start